So we're going to be talking about the development of steam power from ancient Greece to modern times. And this starts with describing a steam engine which I inherited from my grandfather. So I thought I'd just briefly mention him. He lived from 1878 to 1956. So I was 6 years old when he died, so I didn't really know him well, but I do remember him demonstrating a steam engine that he built. He was interested in all kinds of technology, including this bird that sings in a cage. And he had a phonograph, which I've inherited, and it might be interesting just to hear a little clip from that. Considering that was my grandfather's favorite tune, it was probably well worn, but I think the quality is astounding. It has a sapphire needle. This is the steam engine that he built, and when I inherited it quite recently, it was badly battered around, and I didn't think it was going to be safe to use it. So I started building my own. This is based on a design from the Greeks by Heron of Alexandria, which he published somewhere around about 40 AD in the 1st century in a book called Pneumatica. And that book is no longer available, but there were transcriptions made and translations, and they had these drawings showing the machine, but there are at least 3 different drawings. So each time they did another translation, they produced a different drawing, I think. So I don't think we have an exact copy of the original drawing, but he did have it described in words using the letters that are shown in this diagram. And you'll notice here that in the bottom of this caption, it says 200 BC, but recently they decided that he lived in the 1st century AD, and that's because he described an eclipse, and they worked out when that eclipse was. So this machine, this steam engine that he made, was called an aeolipile, ball of Aeolus, and Aeolus was the Greek god of air and wind. This comes from a translation, which is mentioned below, from 1851. And actually, even this drawing here of Hero, that was drawn in the 1500s or 1700s, a couple of hundred years ago. And we really don't know what he looks like, but this is the image you see whenever you're doing your research on Hero. He was referred to as a Greek inventor because he wrote in Greek, but he actually lived in Egypt under Roman rule. He was a philosopher, engineer, and mathematician. Here's another drawing of the steam engine. Hero himself mentioned Vitruvius, who lived about 100 BC, and Vitruvius described an aeolipile and gave this comment: "It was a scientific invention used to discover a defined truth lurking in the laws of the heavens. Thus we may understand and judge the might and wonderful laws of the heavens and the nature of winds." So it was considered a scientific experiment for studying wind. And some people have said that he invented the Hero steam engine, but if you read carefully what he wrote, he was describing a simple ball, a copper ball, with a little bit of water put in through a small hole. It was heated up, and as the water boiled and made steam, he could feel wind coming out of the hole. So they started to understand that wind was actually the motion of a gas. And that was all they got from that stage. They did not have any moving parts or any description of a machine. Hero also described a large number of other ideas and inventions, and this was one of them. It's a machine to open and close the temple doors. And some authors have said this was driven by a Hero engine, but that's not the case. It's a separate design. He had a fire going on the temple altar, and it heated up the base of the altar. As the air in the altar expanded, it pushed down into a closed container of water, and that pushed the water out through a siphon into a bucket. When the bucket filled up with water, it caused the doors to open, and then when the fire went out, it cooled down and sucked the water back in, and caused the doors to open and close automatically. He also described this thing, Hero's wind organ. In this case, the wind was blowing this fan around, and it operated a rocker beam across here, a bit like a beam of a steam engine, and it pushed a piston up and down. You can see the piston here in a cylinder, and that pumped air through the organ and played music when the wind blew. So he knew all about pistons and using it to move air, and you're going to leave this lecture wondering why on earth the Greeks didn't actually develop a more modern type of steam engine and subsequently have an industrial revolution. This is another one of the devices that Heron described was a series of gears. So they knew about gear wheels and how to gear things down, which we'll see later is relevant. This is called a baroulkas and had a gear reduction of 80-1, at least according to that sketch. So here's the one my grandfather built 100 years ago. And this is what it looked like after restoring it. I took it to Peninsula Radiators in Thames, and we took it apart, unsoldered it, and resoldered it back together and got it working. This is an illustration showing the parts of it. We have steam coming up through these vertical pipes and into a hole in the pivot into the sphere. So the sphere fills up with pressurized steam, and the steam comes out through this jet and another jet at the bottom. The jet at the bottom is going to cause a thrust, making the bottom jet move to the left, and the thrust coming from the top jet is going to make the top move to the right, and of course that makes the ball spin around. So we have a spinning ball. And here it is, spinning under steam power. It's sitting on a gas cooker, which is heating the water in the kettle, boiling the water to make steam, and the steam comes out those jets and makes it spin around. Very simple little machine. I'm convinced they actually made it, because when I tried to make it myself, it didn't work unless they did it exactly the way they described it, particularly concerning the bearings. I tried ball bearings and nylon bearings and phosphor bronze bearings, and nothing worked except these tiny little pivots. And here we have the same machine running on compressed air just for convenience, give a bit more pressure and more continuous. Actually, it wasn't very much pressure, I think about 10 pounds per square inch. Now it's ticking over quite nicely until we turn the pressure up. Now this is at about 2,400 RPM, and the limiting factor was it started to shake with being out of balance, possibly as a result of the soldering we'd done on it. I put this slide in here. You're wondering why I'm watering the garden when it's covered in snow. Well, this is actually a modern version of a Heron engine, really. It's using water instead of steam coming out of the jets, and it makes it spin around. It's connected to a gearbox, which makes a little tractor drive across the lawn. The tractor follows the hose until it hits the yellow triangle, and that automatically turns it off. Now, when my grandfather used a kettle, he took the spout off it and put a little plate over the hole where the spout used to be. That seemed obvious enough, and it was polished up. And when we took it apart, we heated it up, and this piece fell off. And look what we found inside, a penny. So that gave us a date, very approximately. It was George V, who reigned from 1910 to 1936, when Hugh Barrett would have been about 32 to 58 years old. So somewhere in that time span he built it, and I reckon it's pretty close to 100 years old. This is my father, who taught me engineering in school, and when the school replaced the lathes that I had learned on, he bought one of the lathes and took it home. And then when he died, I inherited that lathe, and I had to buy a house in Thames to put the lathe in. So here it is in Thames. And I overhauled it and did some mechanical repairs and repainted it. And I used that to start making my own version of a Heron steam engine. This is a design that I came up with. I mounted it inside this hexagonal frame made of stainless steel and brass, with stainless steel nodes on the corners. And here's a little clip of the lathe running. It's a bit noisy. Oops. Oh, I missed. Try again. Okay. Well, that's what a lathe does, shaping things. And I also used it to make the copper parts for the boiler and for the spinning disc. Spinning, well, it's supposed to be a sphere, but I had difficulty making the copper turn around into a complete sphere without buckling, even after annealing it. So I had to make do with these bowl shapes. So the way we do this is you run this as a wood lathe, put a piece of wood in the lathe, and use a chisel to shape it into roughly the shape of a bowl, which is used as a pattern. Then a sheet of copper is placed in front of the pattern and held in place by a skateboard wheel I've got mounted in the tailstock. and then I used the metal bar to push the metal plate against the wood, and it ends up being the shape of a bowl, and ended up with a lot of byproducts of these little bowls. But if you get two bowls and put them together, I could make a spinner. It also made a very nice boiler, which you can see at the bottom here. This part's the boiler and this part's the spinner. And in the water filling cap, I put a coin, just like my grandfather did. So you can see I started making it in 2015. So here is the first version that I made running on compressed air. You can see I've got a pressure gauge on there, reading about 10 pounds per square inch at the moment. And it's also got a pressure relief valve over here that will pop open if it gets over 15 pounds per square inch. I've got a main valve for turning it on and off here, and an emergency valve so I can relieve pressure if it gets too high. 2,800. So you may have heard me say 2,800 RPM. So it's quite similar actually to my grandfather's one at 2,400. Still not as well balanced as I'd really like. Look nice, I think. Put it on the barbecue. And there we go. Now, the object of doing this was to prove that it could do work. So I made a little gearbox for it to gear it down. The problem is that it has very high RPM, so it spins fast, but it has very low torque. Torque is the rotational force that it can produce. And if you want to do any mechanical work, you usually need to get a reasonable amount of torque. So I made this gearbox, which gears it down by a factor of 44 to 1. And so I made the little gear wheel on the lathe and a wormed thread for it to run on, made with a thread cutting tap. And I originally thought I'd connect it up to an Archimedes screw, since that was developed by the Greeks as well. So for that reason, I made it so you could tilt it over. Although I haven't actually made an Archimedes screw for it. Instead, I decided to make a crane. In order to engage this gear wheel, I made this contraption to raise and lower the gear and make it engage, and also it has a brake on it. I then obtained a ball from China, which gets around some of the balance issues. Stainless steel ball, gold-plated, very cheap from China. And so we made this version 4 of the engine. You can see in the very bottom of the picture, the boiler is also modified to put copper tubes in there to increase the surface area so it could produce enough steam. This is what the pivot looked like on the original grandfather's steam engine. And this is the diagram of the pivot that I made. The main difference is that I put a sleeve around it so that if the shaft jumps off the pivots, which has happened sometimes, it'll get captured by this ring and it won't fly across the room. Notice it only has steam coming in from one side and into the ball. The gold part in the background represents the ball. I think I should modify this and put the steam entry from the other side as well to balance it and to give more cushioning of steam on the right-hand bearing, because friction is a problem. So here we have the flying saucer version of it running, and I've made it so it will lift a weight. And the idea of that is so that I can calculate the power output and the efficiency of the engine in doing work. Many people have said that it wouldn't be able to do any work because the torque is so low, but I've got around that by gearing it down. And the Greeks did know about gears. So we see it lifting a bottle of water. There's 200 cc's of water in it. 1 millimeter jets. And this is a typo. It's not 0.55, it's 0.055 watts of power produced. So very small amount of power really, but it's enough to do a little work. So that succeeded in demonstrating that the engine could actually do practical work if it was geared down. A lot of people have said this thing could never be used as a machine because it didn't have enough torque, and I think I've proved otherwise, that it could actually be used. Another video. This is the version 4 with the ball, and also the boiler with the increased service area. Surprisingly, it didn't actually work that much better, except it did get up to 5,400 RPM. And I see it's leaking a lot of steam around the left-hand pivot. I'm using a big spool here to wind the string onto, so that's causing it to slow down to 660 RPM. That produced 0.06 watts. So again, very similar. That seems to be the figure that I'm getting is 0.06. In theory, I calculated in theory how much thrust it should produce, and it was came to 1 watt at 600 RPM. So I was expecting to get about 1 watt, and I got more like 0.1 watts. I hope you could hear over all that noise. There was somebody else who I don't really have to mention, who developed a device for rotating meat on a spit. And a lot of people have said this was a Heron engine that he used, but it wasn't. It was actually a stationary steam jet directed onto blades on a wheel, which was spinning around like a turbine. But that was in Arabic, and it didn't seem to get into the European literature, and doesn't seem to have been developed any further either, a bit like the Heron engine. So the next stage is we're going to talk about using atmospheric pressure to drive steam engines. Atmospheric pressure is 14.7 pounds per square inch. In pascals, which we're supposed to use these days, it's 101,000 pascals. And this little experiment I did on a barbecue in Tennessee.
Empty tin can. We've had paint thinner in it. And we're going to put a little bit of water in there. You know, put it on the gas cooker. Right. And go. So we'll take a little while for that to steam up. Okay, so now I'll put the lid on and heat off. The childproof lid. I think it works. Okay, so it's screwed on tight now, and the gas is turned off. We'll see what happens when it cools down. This will speed it up a little bit. So the steam is cooling down inside and condensing and contracting, and this leaves no air inside, so the container collapses. So it's a steel container.
This was an experiment that was done when I was a third former in high school, and I was so impressed with this. He used a gallon-sized kerosene tin, which completely collapsed. And it's the atmospheric pressure that's doing that. There's no air inside because it started off with steam, which turned into water and made it collapse with a vacuum, really. So the steel container was 112 square inches, giving a total pressure on the container of 3/4 of a ton on that small container. Now, Savery came along and invented a device for pumping water out of the mines using this idea. And what he did was he had a boiler that was producing steam. It did not have to be under any significant pressure. And the steam came into these chambers and filled them up with steam. And once they were filled with steam, he closed the valve from the steam and opened the valve to the mine and let the air, the steam in here cool down and condense into water, and it would suck water up out of the mine. Once it had sucked it up, he closed the valves again and refilled it with steam and repeated the process to pump water. And interestingly, he patented this device. It was the first commercial device used successfully to perform any kind of work, but it didn't have any moving parts apart from the valves, and I wouldn't really consider it a steam engine. However, he patented it as a steam device. It had no piston or moving parts. His patent had no description or drawings. It simply said he used steam to draw water out of the mines, and that was all. And it was patented in 1698 and extended through to 1733. And during that time, people were not allowed to make any kind of steam engine without paying royalties to his invention. there was an interesting comment in a newspaper saying that the quantity of steam raised was so great as to rent the whole machine to pieces, and the engine was laid aside. And that was in 1705. I put the slide up because I want to introduce Dennis Papin. I think he's a key feature in this history. He was a Frenchman, but was a Huguenot and needed to escape from France. So he went to live in London, and he went to work with Boyle. Now, Boyle in 1662 had come up with this law about gases, saying that the pressure times the volume is a constant. So if you have, say, a gas in a cylinder with a piston, and you double the volume, you halve the pressure. If instead you halve the volume, you double the pressure, but that product of pressure times volume remains constant. So Papin worked with him and understood some of these characteristics of gases. Newton's third law of motion, which is used by Hero's engine, wasn't developed until 1687, and Savery's pump came in 1698. To complete the story, there was a guy by the name of Jacques Charles, who had hot air balloons, and he added the temperature term. So PV over T is constant. So that's just a little bit of science that was going on at the time. So here's Papin, or I think it's probably supposed to be pronounced Pape, but I guess I'll use the anglicized version. So he was a French inventor working in London, and he proposed to the Royal Society, and had papers that he presented, so it's in writing, that he proposed these things to the Royal Society, initially talking about using atmospheric pressure. And then he built an atmospheric pressure engine in 1695, and this was exactly copied by Newcomen in 1712. So 1712, Newcomen copied his design and patented it. But Papin never got a cent out of it. I guess he didn't have enough money to take out a patent in the first place. In 1707, he even went further and designed a steam engine using pressure, steam under high pressure. So he came up with all the ideas initially, and even proposed that it could be used to drive water pumps, vehicles, and ships. But he was never paid a penny, and he died destitute. This is a drawing of the little steam engine, or part of it, that he built. It was about 2.5 inches in diameter. Then Newcomen came along and commercialized it, and this is how it worked. We have a rocker beam here, which is going up and down with the engine, and it's connected to a pump on the left-hand side. These T-shaped things represent valves, which are opening and closing to pump the water. We also have valves on the engine, and we'll see what they do in a moment. This one injects water into the cylinder. So we have a boiler at the bottom here with a fire producing steam, and this pink hot steam comes up into the cylinder. It doesn't actually push the piston up. It's very low pressure steam. Instead, the rocker arm simply rocks down simply because of the weight on the left-hand side. So it's not doing any work as the steam comes in. And the reason is they just couldn't make boilers at the time that could handle high pressure steam. So this is what happens when the piston gets to the top. The valves all change around. The valves on the pump have changed, and we open a valve on the water tank, spray some water into the cylinder, into the hot steam that's in there, and then we close that valve, and then the steam that's trapped inside the cylinder starts to cool down, and you can see the parallel with the experiment we just did. Instead of the tin collapsing, it pulls the piston down. As the piston goes down, it lifts the piston on the other side and pumps water. So here we go on a slow version of the animation. You can see the valves opening and closing. Steam going in, squirt of water cooling down, steam going in, squirt of water pulling it down. And each time it goes down, it pulls water up out of the mine. So that's the Newcomen steam engine. And about 1,500 of these were in use before we got to the next stage. And the next stage was when Watt came along, and he was asked to repair one of these machines and realized that he could improve on it. So here's the machine designed by Watt. He paired up with an engineer by the name of Bolton, and they built this machine, which was a lot more efficient. What he realized was that every time you put steam in the cylinder, it had to be hot, and then it would cool down with the spray of water, and you're constantly having to wait for these temperature changes to take place. So he separated these two components, had a boiler out here and a condenser, which was always hot, and the boiler and the condenser was always cold, and it didn't really matter so much what the temperature of the cylinder was. He also used a little bit higher pressure in the steam to use a partial or low pressure system that actually pushed the piston down. So he got extra force from that, and that probably improved the efficiency a lot. So here we go with this model. The pump on the left-hand side is the same. At this stage, we've got steam entering from the boiler on the right-hand side, pushing the piston down. When it gets to the bottom, the steam's turned off. The pump valves are switched over. But there's a bypass track here, and that valve is opened. So now as the piston comes down again, the gas has come out from the top of the cylinder into the bottom without doing any work at all. So this is a really passive stroke of the engine. It doesn't do anything in terms of power. It just transfers the steam from the top to the bottom. And once it gets to the top, it starts cooling down and condensing. And the swirly pattern is supposed to represent the steam condensing into water. Pushing down with steam pressure and the suction from the bottom. In a passive cycle, just transferring the steam from the top chamber to the bottom, coming from here around the loop to here. And now the steam that's trapped in here condenses and pulls the piston down, while at the same time, fresh steam is coming in from the top. So we'll speed that up a bit. This is the animation of the Watts version of the beam engine. Shortly after that, it was modified again and known as the Cornish beam engine. The only difference was that the timing, valve timing they used was injected steam just at the beginning of the cycle. Now, one thing that hasn't been mentioned in that drawing are a couple of features here. Apparently somebody had patented the crank, and so he wasn't allowed to use a crank here without infringing or paying for the patent on that. So he came up with this gear wheel design. He also came up with this system on the left-hand side because the arm coming up and down makes a curve. And that makes the rod on the piston buckle over to one side and makes the piston jam or leak. And so he devised this linkage to make a straight line movement, and he was very proud of that. He said it was his best invention. This is how it works. So you can see that you have two arcs here, and joining the two arcs together makes a straight line. So whenever you see a beam engine, you'll see this complicated looking set of linkages on the end that provides a straight line. Here's an example of let's turn the volume down here. A cross-nest sewage pumping station. I just happened to notice this online the other day and saw this linkage on here and recognized it. So let's take the blue lines out and you'll see it. So that's to get the straight line movement of the piston going up and down. And you can see these are huge machines. There's some people standing down here in the bottom right-hand corner. So this is a sewage pumping station. And it was also used to pump water, beam engines. And this is at Kew Bridge Steam Museum. I've got a couple of examples. And again, you can see this linkage mechanism on the top right, around here. There's two engines in a row here. And this one's actually using a crank. There's another one at the same museum. They ran quite slowly. Newcomen engines ran at about 12 cycles per minute, about 5 seconds per stroke. And this was used right up until relatively recent times, pumping water for London City. So I mentioned earlier that although Watt did use some steam pressure in his system, it wasn't really very high pressure. It wasn't until Fred Trevithick came along that he actually designed some high pressure steam boilers. Excuse me. He didn't use a condenser so as to avoid Watt's patent. And this is what his boilers look like. So there are all sorts of people involved in this whole process of development. In fact, there are more than I've got on this list. But we started with Papin, and Newcomen took over his design and what improved on it. Trevithick came along, and his grandfather built Newcomen engines, so that was his introduction. And his next door neighbor happened to be William Murdoch, who worked for Watt. Now, William Murdoch decided that it would be a good idea to put a steam engine on a vehicle. And so he made a model of a steam car and wanted to patent the idea and start building them. So he talked to his boss, Mr. James Watt. James Watt said, no, this is far too dangerous. These boilers blow up all the time, and I don't want you building anything with high pressure steam. And to stop Murdoch from doing this, he took out a patent on it and didn't build it. So Murdoch was stuck. Fred then worked with Bull on his high pressure steam system. We'll talk a minute about Bull's engine. And I should mention that there were a couple of other people around the world. Oliver Evans worked independently in the United States on similar ideas, and Arthur Wolff worked on strong steam in London. And right at the end of the story, Stevenson and Son came along and developed the locomotive, which we're not going to be talking about today, really. But Trevithick made this puffing devil in 1801. It caught fire when they left it to boil dry, so that wasn't very impressive when they had so many problems with boilers exploding as well. So he was the first to build a full-sized steam-driven vehicle, and this is a reconstruction of it. There was another guy by the name of Cogno who built an earlier engine in 1770, but it wasn't very well documented, so not well understood. Here's a steam engine that Trevithick designed to be used in the coal mines in 1803. Interesting, perhaps, that he put his piston and cylinder inside the boiler to keep it hot, and just had the rod from the piston projecting outwards, and it had little linkages here to the valves to make the valves open and close. This is a Bull's direct-acting steam engine. I think this is a very sensible design. They just cut out the beam. So this had the steam piston connected directly to the water pumps, which are underground. And remember, we talked earlier about the fact that you can't pump water up more than 32 feet by a pump at ground level using vacuum to pump it up. You have to have the pump located underground to go any deeper than 32 feet. So they have the pumps way underground and operated by this rod coming from this piston and cylinder here. And the first big pump at Thames used to pump water out of the gold mines was a Bull's pump. And the site where it was located is under State Highway 25. So I've put some coloring in the diagram here to show how it worked. It was simply applied high pressure steam at the bottom of the cylinder and push the piston up. And as it's going up, the piston underground and the pump pulls water up. The exhaust from this engine was fed then down to another little piston which operated the valves. So Bull's pump in Thames was operational from 1872 to 1895. It was a very large machine with a diameter of 81 inches and a stroke length of 10 feet or 3 meters. So 2 meters in diameter, 3 meters long, and it was the largest pump in the world at the time. There's an article in the Treasury Journal, the treasury.org.nz, about that by Dave Wilton. It had produced 300 horsepower and could theoretically pump 10 tons of water per minute from a depth of 443 feet, as I say, by locating the pumps underground. A&G Price came along and extended it to 660 feet. Now I'm going to talk about different types of engines that use pistons, more like modern steam engines. This is a design that you come across only really in toys. It's called an oscillating cylinder engine. So this is a cylinder and the piston inside it. We have hot steam coming in here through the intake port. So a port is just a hole in the plate behind it, and there's a hole in the cylinder that lines up with it. So the steam will come in through that hole into the cylinder, push the piston down. The piston coming down pushes on the flywheel, making it spin around. When it gets around to the top, by then the cylinder has rocked over. It's pivoted around that red point here. So it tilts over, and now the hole in the cylinder lines up with an exhaust port, and the steam comes out through this exhaust. So here we have an animation of it. Steam coming in, pushing it down, momentum pushing it out, steam coming in, the momentum of the flywheel coming around pushes the piston up, in, out, in, out. And here's the model, a 2-cylinder, twin oscillating cylinders. From there, we can advance to a more sophisticated piston engine, which is called double acting because it works on both ends. We'll see how. Here, the pink steam is coming in from the left, pushing the piston to the right. When it gets there, the steam comes in from the right and pushes it to the left. And this is all controlled by the valve piston at the top. So the valve here is regulating the steam coming in and exhaust going out. Steam coming in from the left, pushing the piston to the right. Steam coming in from the right, pushing the piston to the left. So that's double acting. Now, if we look at the exhaust side, we find that as the piston's coming back to the right here, it's pushing exhaust out through here and out through exhaust line. When it comes moving to the left, it comes out that side. Again, it comes out this side and out through the exhaust port. So that's how a double acting steam engine works. And that's an important illustration because that's really how virtually all steam engines work these days. Here's another illustration of the same system. It has a flat plate instead of a piston doing the valve work, but it works the same way, allowing hot steam, the pink steam, to come in on one side and then the pink steam on the other side, going quite quickly. What I want you to notice here is that we have got an eccentric cam here. So this is a circular device that's mounted off-center on the main shaft, and it causes this thing to go backwards and forwards, and the green shaft is connected to the valve. So this is operating the valve system. If you take that circular disc and move it 180 degrees around the shaft, it'll still work, but the engine will run in the opposite direction because it reverses the valve timing. So you can use that to reverse directions, but this one will only work in one direction because that's not movable. Here's an example of a steam engine. It's a Tangy engine at Gold Mine Experience in Thames. And I've been working on restoring this engine, or helping to restore it, including pouring new big end bearings from molten metal and reinserting the piston and making adjustments. Well, notice this one has a single camshaft, the same as we saw in the diagram, operating the valve system. There's a spinning ball governor, so when these balls spin out with centrifugal force, it slows the engine down. Now this is animation illustrates how the engine could be used in reverse, and this is used on locomotives. Let's hit that running. So the cam in front of us, let's say that's designed for going in the forwards direction, and the way it's set up here, it's virtually the same as being linked directly to the valve system. So the valve system is essentially connected to this cam. However, I don't have it in the animation, but if you move this white point up to the opposite end, up to this end, and connect the valves there, you'll see that the valve starts moving with the cam that's in the background. So that would go in reverse direction. So just by sliding up and down this slot in this arm, you could make it go from forwards to reverse. Furthermore, if you connect it in the central point here, there's a point that is not moving at all. The valves don't move enough to make the machine run at all, and it just stops. So in a central position, it stops. Now, what happens if you go 3/4 of the way up? Well, it now will run in reverse direction here, but only at about half speed, because the valve's not open at the full time. So it regulates how much steam goes into the cylinder. So it's really quite a neat system. It allows you to control the amount of power you're getting and whether it's going in forwards or reverse. And this system's called the Stevenson linkage for doing forward and reverse. And here's what it looks like on an engine. Well, somewhat slow animation, which came from a website by, oops, I lost it there. Okay. So you can see the bar with the slot in it here, and actually when they pull the lever, it moves the bar itself up and down. And this is the linkage going to the valves. So we're now connected to the front cam, But if you pull the lever into reverse and pull it up the slot, then it starts connecting to the other cam at the back in the background. Although rather a slow animation. Here we have a nice little model. It was made in England, mainsteam.co.uk. It's a 2-cylinder double-acting steam engine. Turn the volume up. Very nice, smooth little engine. Notice it only has one valve cam per piston, so it can only run in one direction. I've looked at traction engines because I've been surprised to see that they only have one cam on them, so they can only go forwards and not in reverse. I'm sure there are variations on the theme. So this is Bella Street Pump House, which is the second big pump that was built in Thames, and it has a steam engine which works the same way. So this is an illustration of that double-acting steam engine, exactly the same horizontal design. And they geared it down with this huge gear wheel on a 4-to-1 ratio to make the pump itself run 4 times slower. And in the bottom left corner here, we see the quadrants. And these quadrants are used to connect the pump to the engine to the pump that's underground. Here's an illustration of how that works.
To illustrate how the quadrant pumping mechanism works at Bella Street Pump House. The quadrants are the 2 triangles we see on the left and right, here and here, and they rock in opposite directions. So these rods that go down to the pumps underground are out of sync with each other. So when one's going up, the other one's going down. And the first one goes up, the second one goes down.
And here's an example of a similar thing from Kew Bridge Museum. This one just has a single quadrant. I only assume that they used 2 quadrants in Thames because they wanted to have two pump systems that separated a distance apart. So the Bella Street pump was built 1896 to 1898 actual construction, and it had 10 Lancaster boilers made by A&G Price, and these produced 120 pounds per square inch. They were 9 meters long and 2 meters wide, and they moved these things around with bullock carts in those days. So you can imagine these huge boilers, 10 of them being installed. This pump worked on 3 stages, so it had 3 underground pumps about 100 meters apart. Now we're going to switch gears again and talk about triple acting steam engines, the next stage of development. Whoops. So here we've got our typical double acting steam engine with steam coming from the right, left, right, left, right. Okay, so then we go to a triple acting steam engine, triple expansion steam engine, I should say. They just realized that the steam coming out of that first engine still had some pressure in it. So they took the exhaust steam and put it into another cylinder, but because the steam had expanded, they had to make the cylinder a bit bigger, and also to get the required thrust on the piston, they needed the bigger area as well. And then they took the exhaust from that one and put it into a third cylinder, which was bigger again. And this was primarily used in ships because they wanted to be efficient and not use too much coal. I guess other people didn't do it so much because it's more complicated, but the Earnslaw uses a system, and I went on another steamship in Connecticut that used exactly the same system. And change gears again. This is another device that I inherited from my grandfather, Hugh Barrett. He was, again, an engineer working on stationary steam engines. And this device is used for measuring the power output of a steam engine, or horsepower. And this video explains how it works. This nicely polished device is actually a steam indicator that was owned by my grandfather when he was a steam engineer in New Zealand in the Waikato area. And it's a device that's used for measuring the horsepower output or efficiency of a steam engine. And I don't have a steam engine available, but I've got some strings attached to show you how it works. This section has a pen on it and is connected to a piston and cylinder in here, but this is connected to the cylinder of the steam engine. So the pressure that's inside the piston of the steam engine, or the cylinder of the steam engine, comes up through here, pushes a little piston up here against a spring, which essentially measures the pressure. So the higher the pressure, the higher the pen rises.
At the same time, there is a string here that's attached to a piece of paper on a drum, which rotates around. So, and that's connected to the connecting rod of the steam engine. So the piston goes backwards and forwards, it makes the drum rotate. And meanwhile, the pressure is going up and down inside the cylinder. So this ends up drawing a graph on the piece of paper. And when it's working correctly, the operator can move the pen up to the paper and draw a loop. And that's it.
And this is a little device he used with it, came in the box for measuring the RPM, because that comes into the equations as well. So you put this little device at the, push it against the center of a spinning wheel, and it causes that little shaft on the right to start rotating around. It's connected by a worm gear inside here and makes the dial start moving around. And so you leave it on there for 1 minute and just see how many turns it has taken in a minute. So that's your revs per minute. Very simple little device made by Starrett, who make a lot of engineering instruments. Here So here's an example of it being used on the bell of Louisville. You see the loop it's making. When it's done the loop, you'll raise the pen. And from that loop, you can calculate the horsepower. It's a bit sideways, I think, but this, you can see that's connected up to the connecting rod. So this series of illustrations shows how that worked. So we can see here that the instrument, the steam indicator, is connected to the cylinder on the left-hand side and just records the pressure on the left side, and we get this loop. And then we do the same on the right side. So now we can see the steam indicator connected in over here and creates this loop. So it's basically a mirror image of the other one. So that tells us the pressure inside the cylinder has a piston that's coming down. And this is the actual recording that I found in the box that Hugh Barrett had actually made. And he measured the left-hand loop, gave an average pressure. He drew vertical lines here and just added them all up and averaged it. Found the average pressure on the left side was 40 pounds and the average on the right was 45 pounds, giving an overall average of 42.5. So that's the number that goes into the calculations. And here's a sheet of calculations I'll work through with you. He recorded that it was the New Zealand Brick, Tile and Pottery Company, and this is located in New Lynn, later becoming Crown Lynn. This was recorded on the 11th of March 1907, and when he was recording it, the brick making machine was the only thing that was operational. The spring that he put in the steam indicator had a rating of 1/156 of an inch of movement for every 1 pound of pressure. The diameter of the cylinder he was working on was 13-inch diameter for the first stage. This was actually a double expansion engine, actually. So the small high pressure cylinder was 13 inches diameter and the larger low pressure cylinder was 22. He did these measurements on the high pressure cylinder. The length of stroke was 2 foot and 11 inches, 3 feet, almost a meter. The steam pressure on the high pressure side was 120 pounds. They had no vacuum on the other side. The indicated horsepower that he calculated, probably looking up some tables, was 88.2 horsepower. That's just on the high pressure cylinder. And again, this was a double expanding engine. And the low pressure cylinder gave 32 horsepower, making a total of 121 horsepower. And it was revving at 86 revs per minute. So that's all the data that he recorded there, and that was handy because I could figure out how he did the calculations. He was recording this at New Zealand Brick, Tile and Pottery Company, which I haven't got time to go into a lot of detail, but this is an interesting history because there were dozens of different companies all merging and splitting and things, and it just got very complicated. But this is one of the products, the bricks they were making there, and he was the engineer there, of course. They also made some decorative things. This is a pot planter made to look like a trunk of a tree that they made. And here's a photo showing that the company Crum's pottery still existed. You can see it written on the side of the truck. Looks like probably about 1950 or so. Okay, so now we're going to do some real mathematics. Well, it's not too complicated, and I hope you'll follow through it all right. Just a simple equation where we take these 6 parameters and multiply them together, and I'll explain how we do that and why. So we have our piston here moving in the cylinder. The amount of force that is on the piston can be calculated from the pressure per square inch multiplied by the number of square inches of area. If you do that calculation, it's a 6.5 inch radius, giving an area of 133 multiplied by that pressure. Remember, the average pressure was 42.5. That gives a force of 2.5 tons on the piston. Quite a lot. Well, that's just the force you're getting. And these guys here are trying to push a vehicle, applying a force, but unless they actually get the vehicle moving, they don't do any work. So at least from a physics point of view, the work is actually the force times the distance you move the object. Other people found they could do it with a little less force. And then so you can calculate the force as the pressure times the area. Now work is force times distance. So you multiply by d for the distance, and that's the work done in a single stroke. Power, on the other hand, is the amount of work being done per unit of time. Well, that depends on the number of revolutions per minute that the engine is doing. So we multiply by R for revolutions per minute, and that'll tell you how much work's being done per minute. So it gives us the equation PARD, which is the basis of the equation, really. But we also have to include N, which is the number of power strokes per revolution. So if you've got a double acting steam engine which gets power on both directions, left to right and right to left, you have to put N equals 2. If you have a steam engine locomotive, for example, it has 2 cylinders, you might want to put the number of cylinders in here, which would be 2 for a locomotive, well, with 1 cylinder on each side. So that gives us the equation pardon. And in the next stage, we actually put the numbers in. Oh, but first we've got to think about the fact that we're using peculiar units here, pounds, feet, and minutes. And we want to get watts. So I've worked out that to do the conversion, we need to divide by 43.3. And once you've got watts, you can convert it to horsepower, which was an older measurement of power. Divide by 745 and you get horsepower. So we take all these numbers, multiply them all together, and we get this huge number on the right-hand side, 2.8 million in these peculiar units. So we divide that by 43.3, 2.8 million divided by 43 gives 65,000 watts, which is 65 kilowatts. And that's the type of unit we use in metric for measuring power. If we want to go back to the old-fashioned horsepower units, we divide by 745. We get 88 horsepower, which is exactly what you said on his form. So I figured that my equation worked. So let's see. Let's quickly review the efficiencies of various things. Hero's engine we found was only about 0.1% efficient. Newcomen's beam engine was 0.2% efficiency. Efficiency is taking the amount of heat energy you're putting into the engine and the amount of mechanical power you're getting out. So it's the mechanical power over heat energy that's used. The Newcomen engine was 0.2%. The Watts beam engine got up to 0.7. The Cornish version of it went up to 2%. Modern steam engines are about 7 to 11%. I'll skip that one. The Stirling engine we haven't talked about, 18%. Interestingly, the human body is only 20% efficient in converting food energy into mechanical work. Petrol engines 30%, steam turbines 37%, and diesel engines 40%. And that explains why you see so many diesel engines on the road. Interestingly, because you're only using a quarter of as much fuel, you can expect to have only a quarter of the amount of carbon dioxide being produced by a diesel engine compared with steam. So if we went back to steam, we would have produced a lot more carbon dioxide. This is an interesting graph showing how the efficiency improved over time with all these new developments in design. And they found that it doubled, efficiency doubled every 60 years, which is a parallel to the more modern Moore's law, which found that computer chip power doubled every 18 months. And here's a turbine as an example. I've reached my 1 hour limit, and I think we've pretty much finished anyway. We've got a Stevenson's rocket here, where he used all these ideas to mount a steam engine on a locomotive, and this won him a competition to be the first commercially produced locomotive. Had some interesting features in the design that might be worth mentioning. It had a double acting system. We can see here the valve going backwards and forwards. They took the used steam and injected it into the chimney stack, which increased the flow of air through the engine, which made the fire burn hotter. And then he had copper tubes all through his boiler to improve the surface area and increase efficiency of the boiler. And those features of design are still in the most modern steam engines, basically unchanged, with minor changes, let's say. So that's pretty much the end of the story in the production of steam engines. And I think you'll still be wondering why the Greeks didn't do all this back 2,000 years ago.